Okay, so now we've kind of gone through the quantum numbers. A couple things. So I want to elaborate a little bit on how the quantum numbers give us kind of what's in the periodic table. But I've got a picture here of the kind of pictorial representations of what some of these orbitals look like. So within sublevels where L equals 0, we have s orbitals. The first picture here is the representation of an s orbital, and what the shape represents is the places that represent the probability of the electron's location. So this kind of goes back to the uncertainty principle, right? We imagine a certain value for the energy of the electron, and that means it's somewhere within this shape in terms of its characteristics and properties. Where L equals 1, which we said was a p type sublevel, there are three different orbitals. So the px, py, and pz are the three representations of those three particular orbitals, right? They're directed along axes in kind of a coordinate axis system, right? L equals 2, we said that was what we labeled a d type sublevel. The d sublevels contained 5 orbitals. So there are 5 different representations of what the d orbitals look like within that shell. And notice they get quite a bit more complicated. There are actually f orbitals as well. There's 7 different f orbitals. There's 9 different g orbitals, etc. All with kind of complicated mathematical representations of where might those electrons be. We're going to return to this a bit when we get into chapter 9, because there's kind of another way of approaching describing bonding, where we think about how the orbitals on one atom might overlap with the orbitals on another atom to make bonding orbitals that stretch across the entire molecule. It's called molecular orbital theory. So we'll come back to these pictures. They're not particularly important at the moment for electron configuration, but I think it is nice to kind of see what those orbitals look like as we start to talk about them. In fact, before I switch the papers, let me use the blank spot over here on the side, right? Let's start to build a little periodic table, right? Where can we put electrons, right? We would start with n equals 1, and if n equals 1, that means L is only equal to 0. That is a 1s sublevel. So the first place, the lowest energy place we can put electrons is in the 1s sublevel, right? And that's all that exists in the first energy level where n equals 1. If we go to n equals 2, there's L equals 0 and there's L equal 1, both 2 sublevels within that second energy level, right? N equals 2, L equals 0, that would be a 2s sublevel. N equals 2, L equals 1 would be a 2p sublevel. So we can put 2 electrons in the 2s, right? So 1 orbital in the s's, so 2 electrons can go in the 1s, 2 electrons can go in the 2s, but there's 3 orbitals in the 2p, 2 can go into each orbital, so 6 electrons could go in the 2p. In the third energy level, there will be a sublevel with L equals 0, one with L equal 1, one with L equal 2. So in the third energy level, there'll be a 3s sublevel, a 3p sublevel, and a 3d sublevel. 2 electrons can go in the 3s, 6 electrons can go in the 3p, 10 electrons can go in the 3d, right? Same explanation of how L relates to the values of m sub L and how many orbitals are in each one, and 2 electrons can go into each orbital, right? This continues. N equals 4, right, would have L equal to 0, 1, 2, and 3. So there would be a 4s sublevel, a 4p sublevel, a 4d sublevel, and a 4f sublevel, right? All these sublevels, their corresponding number of orbitals, how many electrons they can hold, all of that is represented in the periodic table. Right? And that's something we'll have to think about in terms of figuring out an electron configuration. Where do all the electrons exist within a particular atom? So let me talk about that a little bit. And let me just say, I'm going to do a couple of examples. I think this is an area where you definitely will want to spend some time with this section of the textbook. It's just impossible to go through every single example. So it may be helpful, in the textbook, there'll be a big table that shows you every configuration. That might be helpful as well, because I can't go through 118 different elements one after another to show you it every single time and every possibility. Now, a couple things. We start to think about electron configuration. This is basically going to be a list where every electron lives in an element. There's a couple things we can keep in mind here. The first is called the Pauli exclusion principle. And that tells us that every electron in an atom has a unique set of quantum numbers. So remember, the quantum numbers describe the energy level, the sublevel, the orbital, right, and then the spin. So since only 2 electrons can be in each orbital, right, if the first 3 numbers are the same, those electrons live in the same orbital, but each of those electrons would have to have a different spin value to be in the same place. Otherwise, the orbital is going to change, sublevel is going to change, or the energy level is going to change. Okay. Now the second one will come into play when we start to fill orbitals. It's called Hund's rule for degenerate orbitals, and in this case, the scientific definition of degenerate is having the same energy. So for orbitals with the same energy, which would mean orbitals within a sublevel, right? There's 3 orbitals in a p sublevel. All 3 of those orbitals have the same energy. The lowest energy is attained when the number of electrons with the same spin is maximized. So as we're populating a sublevel, if we can keep putting in electrons with spin up, or m sub s, the spin quantum number equal plus 1/2, we should, right? And I'll do some examples there. Okay, now, as I mentioned, a lot of this is in the periodic table. So let's look at just a couple of examples here to give you an idea of the nomenclature, right? But we'll also refer to our handy periodic table. And just to give you an idea of the nomenclature, let me just do the first couple elements. Hydrogen, helium, lithium, beryllium, and let's go up to boron just to give you an idea. Right? If we find hydrogen in the periodic table, right, it has 1 electron. That electron is going to go in the first available place that electron can live. That'll be the 1s. So the electron configuration of hydrogen is 1s, and then a superscripted 1. The superscript is telling us how many electrons, right? And then the previous information is the energy level and the type of subshell. So hydrogen has an electron in the 1s sublevel, and there's just 1 electron there. Now, helium, we can put a second electron in the 1s sublevel. So that would be 1s2. But since we can only put 2 electrons in there, because there's only 1 orbital in the 1s sublevel, that's when that one is full. Once it's full, we're going to have to move on to the next one. Now, the other thing we should think about is a picture that describes spin. So for hydrogen, I kind of got my wording in the way there. So let me put the H here. So for hydrogen, since there's only 1 electron, we can visualize that electron by using a little arrow. If the point of the arrow is up, that's m sub s equals plus 1/2. If we point an arrow down, that's m sub s equals minus 1/2. So for hydrogen, if we think about what the 1s orbital looks like, it's just got the arrow pointing up. If we go to helium, though, that second electron would be represented by an arrow pointed down. So still the 1s orbital, but now it's got 2 electrons in there. And this is kind of the representation of the Pauli exclusion principle here, is that these 2 electrons, since they have the same value of n, of L, and of m sub L, they have to have different values of m sub s. So 1 is plus 1/2, 1 is minus 1/2. Okay. Lithium, since we've already filled up the 1s, we go to the next available sublevel, which would be the 2s. So lithium's electron configuration would be 1s2, 2s1. Okay. 4th electron that would come along in beryllium can pile in to that 2s2 sublevel. So 1s2, 2s2 would be the configuration for beryllium. Now, if we wanted to draw this one out, we could draw the 1s orbital and the 2s orbital. 2 electrons go in the 1s orbital, 2 electrons go in the 2s orbital for beryllium, right? And this is a picture we'll want to use for certain types of atoms when we're thinking about things like whether they can be magnetic or not, which is something we'll talk about a little later. Now, for boron, the first 4 electrons are exactly the same as they were for beryllium, 1s2, 2s2, but that second electron into the 2s filled it up. What comes after 2s? Well, there's a second sublevel within the second energy level, and that is the 2p. So the fifth electron that would come along with boron goes into the 2p sublevel. Okay? Now, the 2p's are going to be interesting. So if we carry on to carbon, nitrogen, and oxygen, right, we can think about how adding one additional electron is going to change what's going on here. Carbon would be 1s2, 2s2, 2p2, 2 electrons in the 2p sublevel, right? And you can maybe imagine nitrogen will end as 2p3, oxygen will end as 2p4. This is where Hund's rule is going to come in, because for the 2p, so there's for boron, I'll do it for carbon, for nitrogen, and for oxygen. Right, the 2p is a degenerate set of orbitals, 3 orbitals with the same energy. With boron, there's only 1 electron in there, so it's just going to go in as m sub s equals plus 1/2 in the first available orbital. But when we get to carbon, here's where we'll have to apply Hund's rule. The first electron would go into that orbital, but the second electron would go into a different orbital, because now they're both spin up, right? That's what Hund's rule says, maximize same spin. So we keep them all spin up until there's no other place to put one that's spin up, right? Which would then violate the Pauli exclusion principle. Nitrogen, with 3 electrons in the 2p sublevel, could have 1 in each of those 3 different orbitals, all spin up. But when we get to oxygen, where the 2p sublevel has 4 electrons, right, the first 3 can go and spin up. There's nowhere else we can put one spin up, so the fourth one would have to pair up with one of the previous electrons in one of those orbitals, and to keep from violating the Pauli exclusion principle, it would have to have spin down. Okay? Now, across the periodic table, fluorine would add another electron there. Neon would add the last electron there that would finish off the 2p. Okay? We're going to have to stop there. We'll come back, talk a little more about the periodic table in the next video.